Good morning, everybody. My name is Pooya, and I am a student in the Beckman Institute here at UIUC, working under the supervision of Professor Thomas Huang. And today I'm going to talk to you about facial expression recognition. Specifically, do deep neural networks learn facial action units when doing expression recognition? I don't have any pictures of cats or monkeys or anything like that, but I do have some people making funny faces. So the main goal of facial expression recognition is to, given an image of a person, can you tell if they're happy, sad, angry, something like that? And it basically is just to recognize that accurately. And there are several applications that you could consider. One, for example, is like tailored ad experiences. For example, if you're watching something on your phone and you like this ad and your phone can tell that you're smiling, enjoying it, then it can send you more of those types of ads. Vice versa, if you show a look of revulsion or you think it's really stupid or annoying, then they can stop showing you that. And then there's also robotics, and you have two of my favorite robots over here, C-3PO and R2-D2. What makes them seem lifelike in the films is that their ability to not only recognize the emotion of people around them, but also to respond in turn. So when they can tell that their master is upset, then they can ask him and inquire about him. So it's an appropriate action, and then they feel like a human. And then finally, there's also medicine, where a robot or some system can tell if the patient is in pain or if they're all right with the procedure and decide how to calibrate it accordingly. So all of these systems have two very specific phases. There's one that I call the analysis phase, where it acquires the emotion from the person and is able to recognize it properly, and then the action phase, where given that emotion, it does the appropriate action. We're going to focus mostly on just the analysis because it is a very, very necessary component, and we just want to get that correct. So the main objectives are as follows. First, can we improve model accuracy, do that correctly? And second, once we have used a model to obtain this, the emotion label, can it learn features that are human interpretable, something that we can glean insight from? So previous attempts, interesting, tried to do emotion recognition can be broken up into several categories. The first is a rule-based or facial action unit approach. In the 1970s, while my slides dance, Paul Ekman proposed the facial action coding system, which was basically a way to categorize specific facial motions into 46 different muscle groups. Oops. Okay, it's not moving now. Looks like my presentation is a mind of its own. Great. Okay. So, to the right here, you see several of these action units that were proposed. Action unit 1 and 2, for example, correspond to the brow raising up and down. Action unit 9, I guess it's a little hard to see, is the nose wrinkling that when you like smell something pretty funky or nasty, or you're disgusted. And then action unit 27 is the mouth stretching, jaw when you're surprised. So in the facial action coding system, Ekman proposed that every emotion that you can make can be expressed as a combination of these different action units. But the problem with that is that you need to detect each of these individually with high accuracy, and they're usually handcrafted and really, really brittle. So along came appearance-based methods, which took images as a whole, a more holistic approach, and tried to see how did the can you like look at the textures and the more holistic things. So for example, they would use filter banks of pixels, such as Gabor wavelets, Haar wavelets, or LBP features called local binary features, to give you a filter map and then apply them to the image, just convolve them or correlate them. So they would sweep them across the image like here, and then their responses are what are fed to the algorithm, to a learning algorithm, your favorite one, and try to classify the emotion. And then in recent years, just a few years ago, a really powerful appearance-based classifier has come along called the neural network, specifically the convolutional neural network. It does a very similar thing to these appearance-based methods in that it sweeps several filters over and over again over your image and uses those responses to classify, except the difference is instead of being handcrafted or picked before, these filters are learned. So it learns to the appropriate filters based on face data that are necessary to do the task correctly in a discriminative fashion. What makes a happy face different from a sad face, and et cetera. So in light of this new powerful technique, the main research question is as follows. Can these CNNs improve performance on emotion recognition current baselines, etc.? And if so, what did they learn? Did they learn something that we can perceive and use to gain insight? So the main contributions that I'm going to discuss are as follows. The first is we show that a CNN model that is trained on very commonly used emotion data sets can achieve state-of-the-art performance. Great. And then second, using that CNN, we can try and show that they learn things that actually correspond to things from human domain knowledge. They correspond to the facial action units proposed in the 1970s by Paul Ekman. So the model that we use is, of course, convolutional network, like I said, and it's a 5-layer one. It contains 3 convolution layers, followed by pooling, which takes the response and summarizes it by taking the max in several different regions, and then passes that to the next layer, where you convolve again, pool, convolve, and then pass the 2 fully connected layers, which apply 2 very simple matrix transforms. And the convolutional layers contain 64, 128, and 256 filters each. So now I'm applying all these filters every time given an image. So now we have our model. This is the same model used for all of the experiments. And so we evaluate on the Toronto face data set and the extended Konik-Kanade data set to commonly used. The Konik-Kanade data set has been around for several years. And then when we analyze the performance, we also consider 2 types of regularization. When you train a machine learning algorithm, regularization is always key in order for you to not overfit on your training set and do well on your test set. And the 2 types we consider are dropout and data augmentation. What dropout does is that when an image is passed through the conv layers and approaches the fully connected layer, we turn off each feature with a probability of half. Now you would think, why would you purposefully make your feature not like it was before? But the reason is you don't want the model to focus on very specific patterns. You want it to focus on more general trends and see what is composed upon several images that are happy, what is common to images that are sad, etc. And then data augmentation, what happens is that when an image is given to the network, we perturb it with a random transformation. And the transformations we concern are translations, horizontal flips, scaling, rotation, and pixel intensity changes. The reason this is useful is because if you kept giving it the same images over and over and over again as you train per iteration, then it only sees those images. It can only do so well. However, if you give it a label-preserving transform, as I call it, then you have lots and lots of images of happy, lots and lots of images of sad. And so you have far more data to consider, and you learn a more richer representation. So the results are as follows. With the regular CNN, we get about 79% on Toronto face and about 81% on Konik-Kanade. Applying dropout gives about 3 to 4% boost in both cases, and then data augmentation gives 10 to 14% boost on each of them. So presenting a conceivably infinite set of number of examples is really, really helpful. And then when we combine both of them, we get, to our knowledge, state-of-the-art performance. Okay, so I've just told you that these networks can obtain state-of-the-art performance. That's great. But now comes the bigger question, is did they learn something that's interesting? And so, oh man, this didn't come out as well as I'd like. But there has been lots of works that have tried to examine what neural networks work. And this is one from a couple of years ago where proposed by Matt Zieler at NYU, which the way it works is that at each layer, when an image is passed, one of the filters is response is left on, and all the others are turned off. And then the opposite operation is done, deconvolution. So when you do convolution, it does the reverse operation back to pixel space, and you see what that pixel is responsible for learning. It's a little hard to see here, but for the first layer, it's actually colored edges. So for example, we have green and pink on one side, or blue and orange on another. These were networks that were trained on object recognition. In the second layer, you have combinations of those colored edges, which is contours. And in the third layer, you see more structured things like wheels and faces and things like that. So this gives the question, can this be done for expression recognition? And as it turns out, that is what we tried to do. So we applied this very similar technique for the third layer on the Konik-Kanade data set. And each of these filters, as you can see, learns things that look very much like facial action units in the face. The second layer is actually the mouth, lip, corner pulling, and showing teeth. So it's when they're smiling. The third layer is the brow scrunching that I mentioned, action unit 9, when they're very disgusted. Filter 5 looks like when you're pushing up the chin, they're pouting and they're very sad. And filter 8 over here is when the jaw is dropped, they're very surprised. So we see lots and lots of things that are discriminative patterns because the network was trained discriminative and are necessary for differentiating between somebody's surprised, happy, or sad. So now that those qualitatively look like it, that seems fair, but is there a way that we can quantify this fact? Is there a way we can use our knowledge that they have the label of that action unit and say, oh yes, the spatial pattern respects the label. Fortunately, the Koenig-Kanade dataset is labeled with facial action unit labels, so we use those to verify indeed that the spatial pattern is the same as what is being shown. So the way that we do it is the following. We take the activations of the third convolutional layer and we say the following. For each given filter and each possible action unit, for a considered action unit, we build a histogram over the images that contain the action unit. And then we build a histogram over those that do not. So these are partitioned. These are two disjoint sets. One set of images is the third convolutional layer's responses to with the ones that have it and the ones that don't. The idea is that if the facial action unit is being shown, this filter should be doing different things when it sees it. It should fire high when it sees it and not when it doesn't. So then in order to ensure this difference, we compute the KL divergence. And then we continue to plot this for all the other facial action units. Then we repeat. So for each filter, we have a plot of the KL divergence for each of the different facial action units. And we can see in filter 2, which I said looked like the smile, that is action unit 12, we see all these KL divergences, and it seems clearly that action unit 12 is firing high. And the other two that fire high are 6 and 25, and those are because those are components of a happy face. And then in filter 3, once again, it is action unit 9, the brow of somebody being disgusted. And also similarly here for 17, which is the chin raising, somebody pouting. And then filter 8, you have, for example, somebody's mouth stretched. 25 is high because 25 is also mouth stretching as well. This one is just jaw drop. And then here you have filter 10, which is action unit 1, the brow raising. Action unit 2 is also high because it is the inner versus the outer brow. So they both have very similar appearance features. So finally, to wrap up, if the main question of the talk was, do deep neural networks trained on expression recognition learn facial action units? I would say in this case, for the Koenig-Kanade dataset, it seems to be so. So they can achieve state-of-the-art recognition on the Koenig-Kanade dataset and the Toronto face dataset as we tried. And then finally, we show that indeed, qualitatively and quantitatively, that they appear to resemble the facial action units. And so I'd like to thank all the people who have helped me on this project, both here at UIC, MIT Link Labs, and former lab mates, and my references. And thanks for listening.